Okay, so, yes, we're going to do the binomial expansion theorem, and you're going, what's that? First of all, when you see the word binomial, what's a binomial? To what? What's a binomial look like? We've done a million of them. We factored things into two binomials, but each factor was a binomial. What did it look like? Yeah, it had to have something plus something, something minus something. It had to have two terms in it. So in this case, what I'm looking to get to here, where we're headed, I want to be, if I was to tell you to take x plus y to the 8th power, right now, what's the only way you guys could take x plus y to the 8th power? No, I actually want you to work it out. That's x to the what power plus whatever times x. What does it mean to take something to the 8th power? Times it by itself 8 times. So it'd be x plus y times x plus y times x plus y times x plus y, and keep going 8 of those. You want to boil 8 sets of those together? That would be horrible. Horrible beyond horrible. As an absolute nightmare to work that out. So mathematicians went, okay, when we need to do big powers on a binomial, we are not going to work all that out. We need to find some other way. So somebody got to playing with it and noticing there's a pattern that happens when you're working with binomials. Okay, so what you're looking for is, actually there's more than one pattern that happens here. If I said take a binomial to the 0 power, what's anything to the 0 power? 1. Okay. And if I said take it to the 1st power, x plus y to the 1st power is x plus y itself. Okay, that was pretty boring. And if I said take x plus y to the 2nd power, we know how to do that. You can FOIL those. Can anybody FOIL it in their heads? Yes, it would be 2xy's, because you get the same, outer and inners would be the same thing twice. And then y squared, if you FOILed that out. Okay. But then, if I threw you x plus y cubed, and I said, okay, work out that, you'd have to take this answer we just got up here, the squared one, and take it times another x plus y. And suddenly this is starting to get kind of nasty. And if I keep going up, it's going to get really nasty. Well, like I said, you're looking for a pattern. Since I know the binomial expansion theorem, I'm going to write out for you what you get here, if you actually work this out. You guys are looking for the pattern. Oh, that's x squared, yes. That's y squared. And then let me give you a 4th power. That'll give you a little more to look at. That'll be x to the 4th. That's a lot of terms. That's the question. How am I getting this? Okay, so let's break it down one pattern at a time. Look at the x's. What's happening to the x's on every one of those? Yeah. The x's, if this was 4th power, we start x to the 4th, 3rd, 2nd, 1st, 0. What did the y's do? Where did they start? They actually start here. What's this is y to the what? That's y to 0. 1, 2, 3, 4. So your x's went down a power, your y's went up a power. What do you notice about the sum of the powers on the x and the y together? Yeah. 3 and 1 equals 4. 2 and 2 is 4. 1 and 3 is 4. 4 and 0 is 4. So on this one, all the sums of the powers are 4. What happened up here on the cube? They're all 3. Because 2 and 1 make 3. 1 and 2 make 3. So they all sum up to 3. You'll notice when we were doing squared, all the powers add up to 2 every time. That's always true. So if I have you do x plus y to the 5th, or we eventually do it to the 8th power. If we do the 8th power, then x's and y's will always add up to 8. Their exponents will, every time. So that explains what happens with the variables. But yeah, where did I get the weird numbers? Why is it 1, 4, 6, 4, 1? Where did those coefficients don't look like they got a pattern. Maybe 1, 3, 3, 1 maybe looked a little better at the third power. You thought maybe there's something with the 3s. But yeah, why a 6? Well, has anybody ever heard of Pascal's triangle? We love Pascal's triangle. Pascal is, well actually, he's a famous mathematician. He's also famous in sciences. He did a lot of things, particularly in physics. But in math, he's actually the guy you have to thank for developing the actual true probability theory, for making probability be a study in mathematics. He's the first guy who really seriously went into looking at probability. So, yes, every time you're doing your homework, say, thank you, Blaise Pascal. Talk about Pascal?
Oh, he did. And then I heard a whole bunch of numbers in it.
Yes, the triangle.
Oh, yes.
Did he show you how to do Pascal's triangle?
Yes, he tried to do it.
Okay.
The triangle was like had so many numbers in it. Yeah, he tried to do it, and I'm pretty sure he lost it at the first number. So.
Okay. His triangle starts with a 1, and he always keeps 1s on the outside edges. So row 1, the very top row is a 1. So then the next row you add a number on either side of it, and you still have 1. Okay, here I keep keeping 1s on the outside, but the middle number is a 2. Can you figure out why? The 2 numbers above it, the 1 and 1 above it, to go together to make 2. So the next one, I keep a 1 on the outside. The 1 and the 2 make 3. 2 and 1 make 3, and then a 1 on the outside again. So now what's the next row? 1, 4, 6. You just keep adding the 2 numbers above you to make the number you need. And then the next one would be 1, 5, 10, 5, 1. And so how do those numbers remind you of what you see over here in all these binomials we expanded? Yeah. You'll see 1, 2, 1 right here in the square, in the binomial squared. We had 1, 2, 1. The next row we had the cube, 1, 3, 3, 1. There's 1, 3, 3, 1 in your row of Pascal's triangle. Now, what they actually did though, so that this will all correspond, they call the top row row 0. So that's what you get when you take it to the 0 power. So then the second row we see is actually considered to be row 1, because that's what you get when you're at x plus y to the first power. So then we would have row 2, etc., going down. So you could work this out. You can work out the triangles as many rows as you want to work out the triangle to and find any pattern numbers. Now here's the actually other amazing part. Those numbers in that triangle are all combinations. They're all numbers you get from doing combinations. And in fact, more miraculously than that, it's actually this row 5, since it's row 5, this is all the combinations that start with a 5. That 1 is what you get when you do 5C0. 5 is what you get when you do 5C1. 10 is 5C2, and it's also 5C3. Both of those give you the same answer. This is 5C4 and 5C5. So row 5 is all combinations that start with 5. Row 4 is all the combinations that start with 4. So every single number in there is one of the numbers you get from doing combinations. Yeah, I'm excited. Okay. We could actually spend days, and days looking at Pascal's triangle. I have here, this entire book is about Pascal's triangle alone, and all all the patterns that are in it and all the different sequences and things you can do with it. Pascal's triangle. There's oodles and gobs of patterns. And you can see on this book, if you, I'll pass it around, you can see how big the numbers go on the triangle pretty easily. I'll also get my posters up. That I have several posters about Pascal's triangle. Okay, a couple patterns that are easy, quick to see. You'll notice you have two diagonals that start out at the top and go 1, 2, 3, 4, 5 right down the diagonal, both ways. One of my favorite patterns is the pattern they call the hockey stick. Because what you do is if you start at any one of the ones on the outside and you go diagonally, so say I come down this diagonal here, 1, 3, 6. If you add up 1, 3, and 6, what's the sum of 1, 3, and 6? Your answer will be what's diagonally the other way. The answer is 10. And if you circle it, they think it looks like a hockey stick. So it doesn't matter what diagonal you pick. If I had picked the 1, 2, 3, 4, its sum is 10 too. So any diagonal you go, when you start at one of the ones, any diagonal you choose to do, and then you cut back the opposite direction, you'll get the total of that particular pattern. And then there's all kinds of, I'll put my one up with designs. They started, sometimes they'll take this and they'll black out certain numbers if they fall in certain, what are called triangular numbers, and all kinds of different types of numbers. When they start looking through there for a number analysis of all the numbers in there, you can find all kinds of patterns. Just, like I said, we could do days and days on Pascal's triangle alone. But for us, yeah, it's giving us these coefficients. And in a little bit, believe it or not, I am going to turn this whole idea of this expanding these binomials into what's called binomial probability. And what you can do here with x's and y's, we can then use to calculate probability here shortly. It's not that major thing. Okay. So the problem is, though, I'm not just going to give you x plus y. I might give you x plus 2y, or 3x minus 4y. Don't cry, it's not that bad. They actually, at first, they whine at me about this, and then the next day they come in and go, can we have more of those? Put more of those on the test, because they think these are easy once you've done a couple of them and find it's not that involved. So we are going to do here 3x minus 2y to the 4th power. So if you're doing 3x minus 2y to the 4th power, I want you to expand this out. Find what all the terms, this would be something x times something y plus something x times something y. We're going to expand this thing out. What was the pattern that happened on the x terms? What were the x terms doing back here? They were going smaller every time. Actually, I'm going to stop this recording in a second because this is going to take a long time and this is